Alright, so we're looking at specific heat capacity here. And specific heat capacity is basically a way of identifying, well, if we add heat energy, how much will the temperature change? As we've already looked at, heat and temperature, they're just similar things, but they're not measuring exactly the same thing. Okay, so we've got this equation for specific heat capacity. Q equals M times C times delta T. Now, a reminder that delta T means changing or difference between. So I'll show you what these letters stand for, and then we'll go through an example, just a simple example on what specific heat capacity can be used to help us find. So Q stands for heat energy. Now, as we know that heat energy is measured in joules. So the standard unit for this is in joules. Our M stands for our mass, as you may or may not have guessed. Okay, and that makes sense. Obviously, the more mass we have, the harder or the more energy that's required to raise the temperature. C is our specific heat capacity. Now, this is probably, for some of us, the first time we've heard this term. And this is basically that each material has a certain amount of energy that's required to change its temperature. That's different for every material. There are a few that we like to learn off by heart, but generally this won't be an expected value. So the specific heat capacity usually will be given, and it's usually given in the unit of joules per kilogram or joules per gram, depending on the type of question. And we'll run through that in a second. And delta T is the difference or the change in temperature. Okay, and that can be measured in either degrees Celsius or degrees Kelvin. Now, that is defined, delta T, as TF minus TI, which is our final temperature minus our initial temperature. Okay, so I'm going to go through an example and try and show us how we can use that equation to help us identify whether a heat will cause temperature, how much temperature change we can expect to see given a certain amount of energy. We know that M is our mass, so I'll just run through the question here. We've got 1,000 joules of energy is applied to a cup of water that starts at 25 degrees. What is the final temperature? Okay, so we've been given a few pieces of information. Obviously, joules is our energy. That's our initial temperature. And 250 mils, although it's not a unit of mass, we know that 250 mils of water is equal to 0.25 kilograms, or 250 grams of water. Now, I'm using grams in this scenario, and I'll show you why in a second. Our Q is 1,000 joules. Well, 1 more 0. So we've got 1,000 joules. Our specific heat capacity is 4.184 joules per gram. Now, in black, I'm going to write 4.184 joules per kilogram. So that was given. So this value here, I'm just going to make here, that's given. As you go further through, you'll be expected to know the specific heat capacity of water off by heart, not in physics, but in chemistry. At this stage, I'm going to give you those values. So you've got 4.184 joules per gram. That is exactly the same as 4,184 joules per kilogram. But if I represented my mass as a kilogram, that would be 0.250. And you will see that the decimal place movement will cancel out. The decimal place here moves back 3, the decimal place moves forward 3, and vice versa for our kilograms. Now, our change in temperature, we don't know, we can find our change in temperature, but that again is going to equal TF minus TI, and that might come in handy later on. Okay, so I'm going to apply this to I'm going to come back over to this side of the board and apply this question to our formula. So we've got Q equals 1,000. M equals, I'm going to use the grams in this scenario, not the kilograms, just because it's a little bit kinder. So I've got 1,000 equals 250 times 4.184 times delta T. And at this stage, we can see the importance of rearranging. We need to get these values to the other side of the equation. I'm going to do them one at a time. 1,000 divided by 250 equals 4.184 times delta T. I didn't run my calculator today, so we've got 4 equals 4.184 delta T. Delta T equals 4 divided by 4.184. Okay, that's going to be somewhere near 1. I haven't got the exact amount because I didn't bring my calculator. Delta T is going to equal approximately 1 degree Celsius. And that doesn't mean it matter if it's 1 degree Kelvin or 1 degree Celsius, because we know that those units for temperature go up by the same amount. It's just their starting point that changes. So I'm going to come back to this equation now over this side. We know that T, delta T, is equal to TF minus TI. We already know our T initial. So TF we don't know, but we know our TI is equal to 25 degrees Celsius. And we know that this is approximately 1 degree. If I rearrange that equation, I add 25 to both sides, I get TF equals 25 plus 1. And I get my final temperature is equal to about 26 degrees Celsius. So the water has changed in temperature 1 degree, which means my final temperature is about 1 degree Celsius. That's the sort of thing we can predict in a perfect scenario with this equation Q equals mc delta T. We'll see that we can apply this to materials exchanging temperature both ways later on, but for now that's a pretty good starting point.